start today's talk. So, good evening, everyone. I am Jung Lee, the Vice President of EQS and Joint Seminar Manager of QISCA. It is my pleasure to introduce today's speaker, Wonseok Huh from EQS. Wonseok Huh is currently a junior for Department of Physics in KAIST and lab member of Quantum Optics and Quantum Information Lab led by Professor Wonseok Huh. Today, he will be presenting a talk titled Entanglement in Linear Optics, sharing insights from the paper Optimal Estimation of Entanglement and Discord in 2-qubit States, Verzi et al. Please join me in welcoming Wonseok Huh to the stage. Okay. Hello, my name is Wonseok Huh, and the title of the paper that I'm presenting today is Optimal Estimation of Entanglement and Discord in 2-qubit States. So this is the abstract of the paper that I brought. Actually, I originally intended to give a general lecture on the notion of entanglement and how to create them and control them in linear optics setup. But I configured that it would be better to select a certain paper and focus on this paper while I express and explain the supplementary information along the presentation. So let me first read the abstract of this paper. I think it's better to give you some time to read this for 1 minute, maybe 30 seconds, yes. You can see some familiar keywords such as entanglement and 2-qubit system, quantum information process, and maybe some of the notions such as quantum discord may be unfamiliar, but it is not really quite relevant to the focus today, so you don't have to give too much attention to it. But anyways, the contents will be presented in the following order. And let me go into the introduction. Recent research in quantum information science requires quantification of quantum resources, such as entanglement and quantum discord. I'll explain what entanglement and discord is in the next slide. Although quantum state tomography can reveal the full information of a quantum system, it is very impractical for higher dimensions, and it also needs additional processing for quantification. So because of this reason, direct measurement of entanglement has been implemented, such as entanglement witness, Schmidt number, Bell test, etc. And in this paper, the author introduces optimal estimators for 3 parameters that quantify entanglement. And these are negativity, log negativity, and concurrence. And in addition to these 3 parameters, they also quantify quantum geometric discord, which I will briefly mention in the next slide. And also the experimental implementation and the results are also presented. I'll explain the notion of optimal estimators and other supplementary background contents parallelly. First, the most basic and fundamental notion in this paper is the quantum resources. Most famously, quantum entanglement, as you all already know, are states that cannot be expressed in a separable state, mathematically expressed like this. So an example of the entangled state will be 1/√2 of 0, 0 plus 1, 1 in a 2-qubit state. And this is the famously called Bell state. And if we make this notion into a larger scheme in a mixed state, then entangled states are non-separable states that cannot be expressed in a mathematical form like this. So in general, determination of entanglement is quite difficult to do because for mixed states, it is known to be NP-hard problem. But for pure states, it is quite easy to determine entanglement. And for 2x2 and 2x3 dimensions, there are some criteria called positive something transpose and entanglement witness. So there are a few ways to estimate the entanglement even in larger dimensions. And most importantly, quantification of entanglement, or in other words, how much the state is entangled, can be determined in several notions, including entanglement entropy, negativity, concurrence, entanglement cost, etc. There are many others. And among these, this paper deals with entanglement entropy, negativity and concurrence. The second notion is quantum discord. This is a little bit more recent and unfamiliar notion, and I actually do not know much about it, but I just brought some information from Wikipedia to briefly mathematically go over this. So in information theory, there is a notion called mutual information, defined as IA times B equals information entropy addition and the subtraction of the both of the mutual information. Anyways, mathematically expressed like that. And in a quantum regime, they are replaced by density matrices and expressed like below. So you don't need to remember the mathematical expressions, but the physical meaning is basically measure of non-classical correlations between two subsystems of quantum system. And this is hard to calculate computationally in this notion. But there are some ways like quantum geometric discord, which can quantify the notion of quantum discord, which will be explained in a later slide.
In the first equation, the mutual information A and B is equal to J A and B. How was the difference of that?
So I cannot give a full physical meaning, but in a classical regime, I think the I and J matches in value, but in a quantum regime, they can differ according to the definition. Yes.
J is quantum regime and I is the classical.
The I and J is defined a little bit differently. They both define mutual information, but mathematically a little bit different. But they can be different in a quantum regime.
Those two expression of the mutual information, and like in the classical case, it is same always. But in the quantum case, we can observe some cases like these two are different.
Nice.
Entanglement or something.
Yeah. And one question, like, is it like while exchanging A and B, is the IAB is fully symmetric, but is J symmetric for the quantum cases? And like for the discord, like I minus J should be same for the pair of A and B, or is it changed for the exchanging A and B?
In terms of density matrices, it is this expression, right?
Yes.
So is this symmetric? I'm not quite sure. So I think you may look it up on the internet for more information. Anyways, before we keep going on with the paper, I need to explain some background information. And the first is feature information. The PPT slides are made by Professor Wonseok Huh. Yes. He is my lab professor, and also he teaches quantum information 1 and 2, or P8, 4, 7, 5, and 6 in physics department of KAIST. So thank you, professor. Anyways. So according to this good lecture PPT, this is basically a lecture about quantum metrology. In a big sense, quantum information science contains 3 big categories, which are quantum communication, quantum metrology, and quantum computation. I guess all of the audience are already familiar with quantum computing. And quantum communication includes quantum key distribution, quantum secret sharing, quantum teleportation, and others. And finally, quantum metrology might be unfamiliar, but it is most widely used in gravitational wave detection. So I recall that maybe in 2016 or 17, gravitational wave detection got Nobel Prize using LIGO. And LIGO is basically a Michelson interferometer that minimizes the noise to detect even the smallest space fluctuations from gravitational wave. And this is possible because we can minimize the noise using quantum metrology, where squeezed light is inserted into the Michelson interferometer. And so this is why we need to learn about the metrology. And feature information is one of the notions in metrology. So basically, it is, in other words, parameter estimation. So basically, we want to measure some unknown physical quantity, phi, and we have the corresponding experimental setup and the detector. So each time we conduct the experiment, we will obtain x1 and the second repetition x2, and from n times repetition xn. And from all of the repetitions, each x1 to xn might differ, because even if the parameter is fixed, there are inherent uncertainty because of Heisenberg uncertainty relation. And also the detector and the experimental setup might not be exact. So this can be expressed by a conditional probability P x dash phi. So this represents the probability of obtaining result xn for nth repetition, while the physical parameter is fixed at phi. So suppose we have a fixed experimental setup and the unknown parameter phi and the measurement, then we can calculate feature information defined like this. It is a function of phi, represented as large f, which is basically the expectation value of this complicated mathematical form. This can also be expressed like this. So if we have a fixed experimental setup, we have a fixed feature information. And also, mathematically, we can prove that Cramer-Rao bound, which is the uncertainty of the measurement phi, which can be minimized to the lower bound of 1 over square root repetition times multiplied by feature information. So once we have a setup, we have the fixed feature information, and we have the lower bound of the uncertainty for each experimental trials. And the proof of Cramer-Rao bound is mathematically expressed like this. Maybe you can take a picture, although it is Professor Young-Sik Ra's PPT. Yes, I'll give it maybe 5 seconds. Yes. Might seem a little bit complicated, but if you go through it, you can easily understand it. But I will not deal with this in this presentation. It takes too much time. Okay. Next. So in metrology, I said there is a lower bound to the uncertainty or precision of the value we want to measure. And we want to make a mathematical expression from the nth repetitions to estimate the actual value phi. And it is done by setting up the optimal estimator. And these optimal estimators must saturate the inequality of Cramer-Rao bound to be optimal, and they must be unbiased. And examples of these optimal estimators are maximum likelihood estimator, which is the most famous one, and Bayesian estimator or method of moments. So yes, and next is quantum parameter estimation. So far, we dealt with classical information regime where we define feature information and Cramer-Rao bound. However, in a quantum state system, we can replace the probe with density matrix rho, and the interaction or the experimental setup can be expressed by quantum channels epsilon. And finally, the measurement will be done by POVM or positive operator valued measurement. And we can decide what kind of measurement to make. For example, we can do some type of projective measurement or do other POVM measurements. And by making the measurement setup optimal, we can saturate even farther, called quantum Cramer-Rao bound. So once we set up the optimal estimators to saturate this inequality, we then set up the measurement and optimize it in order to obtain even a lower bound. And this is mathematically defined by 1 over square root of repetition times multiplied by quantum feature information represented by h. And this is mathematically defined like this. Yes. So in summary, this is the table of how we can saturate each inequalities. First, once the experimental setup probe, measurement setup, and estimator is given, we have a fixed uncertainty. Fixed setup. And then we can saturate the Cramer-Rao bound by choosing the optimal estimator. And then quantum Cramer-Rao bound by optimizing even farther the measurement setup. And finally, if we optimize the probe, or the measurement input, we can get standard quantum limit. And finally, the Heisenberg limit if we optimize this in a quantum regime, for example, using entanglement or squeezed light. So far we dealt with the notion of Fisher information, quantum Fisher information, Cramer-Rao bound, and quantum Cramer-Rao bound. So we will use these notions to go back to the paper that I told you and see how the authors calculated these properties. So in this paper, they set up the input state as this density matrix, defined like this. And this is basically a probabilistic mixture of this Bell state and a classically mixed state. So with probability of P, we have the Bell state, but with probability of 1 minus P, we have a separable state. So yes, and we can calculate each quantification, negativity, log negativity, concurrence, and quantum geometric discord from this state. And the results are in the following order. And before we calculate this, let me just briefly go over what each notion is. Negativity is defined as the partial transpose norm minus 1. And this defines one of the ways to quantify how much entanglement it is implied in the quantum state. Log negativity is simply the logarithmic version of negativity. And concurrence is a little bit more complicated because it is mathematically expressed like this. Anyways, you can calculate it using computers or hand calculations. And finally, quantum geometric discord is defined like this. And you can refer to this notion of discord in the paper below. So from these quantities, we can calculate each quantity for this input state given like this. So for the probabilistic mixture of Bell state and this separable state, we obtain negativity to be 2p times square root of q times 1 minus q. The square root is, I don't know why, but cut here. It should be, line should be over these quantities. Log negativity obtained like this, concurrence like this, and quantum geometric discord like this. And we learned about Fisher information and the Cramer-Rao bound previously. So each can be calculated like this. This has the same result as negativity. And finally, this. And from that, we can also obtain the quantum Cramer-Rao bound, like this inequality. This one has the same result as negativity. And finally, this one. And so these values right here are the lowest bound that we want to get when we conduct the experiment. So how do we estimate this choosing the optimal estimators? In the paper, the author represents two types of estimators, N1 and N2. L1, L2 for logarithmic negativity, and Q1, Q2 for quantum geometric discord. And each one represents the non-optimal estimators and the optimal estimators. So how do we theoretically verify they are optimal or non-optimal? And you can do this by calculating the Fisher information that we just learned. So the author presents the calculations in the supplementary information. We will not deal with the calculations here. And anyways, each one denoted by indice of 1 is the optimal non-optimal estimators. Wait. Yes. Indices of 1 are non-optimal estimators, and those with indices of 2 are optimal estimators. So these, when theoretically calculated, saturate the Cramer-Rao bound, but these ones obtain larger uncertainty than the Cramer-Rao bound. So they do not saturate the inequality. So the author wants to experimentally also verify whether these optimal estimators indeed give better results than the non-optimal ones. So they use linear optical setup to conduct experiment and calculate the results uncertainty using optimal and non-optimal estimators. This setup might not be familiar if you do not work in the optics lab, but I will go over briefly. And in the next slides, there are optical compartments explanation. So first, mode lock laser is used at the as titanium sapphire laser centered at 808 nanometers. And from second harmonic generation, which is a nonlinear optical process, they produce 404 nanometer laser. So it is expressed in blue. And when they go through BBO crystal, a spontaneous parametric down conversion process produces, again, 810 nanometer photon pair in these conical trajectories. And they are entangled in polarization and momentum regime because of the inherent property of nonlinear crystals. And these entangled pairs go through BBO crystal to compensate some spatial delay between the two photons. And finally, from this entangled 2-qubit pair, we do quantum tomography using quarter half wave plate and PBS, or polarizing beam splitter. You do not have to know how these measure tomographic setup, but it is well known that the series of quarter half wave plate with polarizing beam splitter can measure all 16 bases of a 2-qubit polarization state. So this is a well-known setup. So for example, by changing the angles of the wave plates, 16 different bases, we can measure all the bases. And from that, we can obtain the density matrix of the wanted quantity. And finally, single photon detectors, SPAD in this case, are used to measure the coincidence counts between the two outputs. So briefly going over the optical setups. First, spontaneous parametric down conversion is a nonlinear optical process. You may have heard of second harmonic generation, where when a photon is incident on a nonlinear crystal, two photons produce one photon with half the wavelengths of the original ones. So this is basically the opposite of second harmonic generation. In undergraduate electromagnetics course, you may have learned displacement field polarization indicated by the equation D equals epsilon times E plus P. But in the undergraduate course, we generally treat until the linear case, where P is correlated to E in a linear case. But if we enlarge the electrical field, we can observe some nonlinear effects, and it is represented by chi2 coefficients. So for example, P equals this coefficient times E to the square. So these types of nonlinear process can produce two photon pairs from one. And this is called spontaneous parametric down conversion. And they have some limitations, which is that they must have conserved momentum and also conserve the energy. So the frequency of the signal and idler photon pairs are fixed, where the addition of these two must equal the pump power frequency. And the momentum must also be conserved. So in experiment, there are two types of this SPDC process. Type 1 basically produces the photon pairs in two overlapping conical shapes, trajectories. So the entangled pairs can be obtained at this and this point, or in this and this point along the trajectories. And if we conduct different types of momentum conservation, we can obtain type 2 SPDC, where the two conical shapes are matched at different angles, and the entangled photon pairs can be obtained here and here. Next is the wave plates. It is basically a optical compartment that can change the polarization of an incident wave. For example, suppose we have a 45-degree linearly polarized light, but in this wave plate, each angle has a different index of refraction. So for example, along the vertical line, this component goes faster, while along the slower line, they move slower. So after going through the wave plate, they have a different polarization. So the reference of these diagrams are Eugene Heck's Optics 5th edition. And according to this textbook, we have a difference in phase of the two vertically different linear polarization as this one. So NO defines the index of refraction of the ordinary wave, which is light that has a polarization in parallel direction with the optical axis, while extraordinary rays have vertical ones. I mean, the vice versa. So for example, half wave plate can change the linear polarization to some degree, depending on the width of this plate, while quarter wave plate can change between circularly polarized light to linearly polarized light. So these are often used in optical setups. And lastly, polarizing beam splitter utilizes birefringence in an optical regime. So for example, this crystal has an optic axis in this direction, the vertical direction. And when light that has both polarization is incident on this one, this dot and this arrow has different index of refraction. And at this point, one of them is internally reflected and one of them passes through because they have different index of refraction. So this can be used to pass the horizontal polarization and reflect the vertical polarization. So depending on the polarization, we can divide the incident rays into two directions. This is the basic principle of PBS. And this is a short diagram for difference in index of refraction for each polarization. And finally, the experimental setup uses single photon detector. There are a few examples such as SNSPD, SPAD, or PMTs. PMT is the most easily understood single photon detectors, where very weakly attenuated light, including few photons, are incident, and they hit these diodes multiple times, and each time the photons are multiplied a lot, and they produce electrical signals that we can detect them as photon detection. And this one, SNSPD, is superconducting nanowire single photon detector, and they use superconducting properties. And SPAD, single photon avalanche detector, utilizes semiconductor and their electrical properties to detect very low attenuated lights. And in this experiment, the author uses SPAD. So back to the experimental apparatus. Second harmonic generation and SPD's process is the nonlinear process that I explained. And the entangled photons are collected through the wave plates, PBS, to be detected by SPAD. And the coincidence counts can reveal the quantum state tomography. And these are the results. Before going to the optimal and non-optimal estimator calculations, the input states are first verified if they are indeed statistical mixture of Bell state and a separable state. Then how do we create this state experimentally? It is very hard to make this specific density matrix, but we can use statistical post-processing. For example, let us conduct 10 repetitions in an experiment. One set is 10 repetitions. Then suppose we chose P to be 0.5. Then from that 10 repetitions, we send 5 times the Bell states of this right one and 5 times the separable state of this left one. Then if we combine all 10 repetitions, we can say that we have sent a statistical mixture of these two states. So the author creates the input state in this way. Each state is verified to have fidelity of 0.975 and 9.5 for the entangled and separable states. Notice that fidelity is calculated like this, and this represents how close to the theoretical value the quantum state is. It is the closeness between the quantum states. So closer to 1, it means that we have the wanted ideal state. Experimentally, I can say that over 0.97, it is quite high. It's, for optical setup. So this is the final calculation of the optimal and non-optimal estimators. They chose 10 estimators. no, 10 repetitions as one set, and the expectation value and their so each experimental results are represented by the dots here, and their uncertainty as the error bars in these large vertical lines. And the curvature represents the optimal and non-optimal primal row bounds that we calculated in the previous slide theoretically. So we can see that for non-optimal estimators, the uncertainty bars match the outer curvature. And for optimal ones, they match the inner curvature, which is the Cramer row bound. So from these results, for all negativity, log negativity, and quantum geometric discord, you can say that the experimental results match well with a quantum Cramer row bound theoretically calculated by this author. In conclusion, we performed an experiment to measure some non-classical quantum parameters, 4 of them, which are negativity, log negativity, concurrence, and quantum geometric discord. And optimal, non-optimal estimators were suggested for comparison. Optimal ones theoretically saturate the quantum Cramer row bound, and experimental results match well with these theoretical calculations. State of interest was statistical mixture of Bell state, singlet state, and completely mixed state by parameter P, which was produced using statistical post-processing. And finally, results show strong and practical advantage of optimal estimators over non-optimal ones. Yes, so the final conclusion of this paper is that they suggested mathematically the optimal estimators that saturate the quantum Cramer row bound, and experimental setup matched well with the results. So far, this is my presentation. Thank you for listening.
And the author showed kind of optimal one and the non-optimal one. What was their kind of criteria for choosing the non-optimal one?
Non-optimal one, they do not specify why they chose that kind of equation, but it does not saturate the inequality. So I think they just devised some equation that does not saturate the inequality.
So it's kind of set up that it's kind of very realistic for the experiment and does not kind of deviate a lot from the optimal one.
Yes, yes. 네.
한국말
아, 예, 예.
그런 그 퀀텀 그 피셔 어떤 그
네.
어떤 옵저버블 같은 거에 베리언스가 피셔 인포메이션 뭐 어떤 그 구동식에 극한이 되는데
네.
그거보다 더 작게 갈 수는 없고
네.
근데 그 양자적으로 가면 더 작아진다는 건
예, 그쵸.
양자 영역에서 그 고전 영역을 뚫고 더 작아질 수 있다는 말씀이신 건가요? 이게 더 작아질 수도 있다? 사실 사실 로어 바운드를 구하는 거에서
그러니까
커지는 의미가 있는 건데 작아지면
그러니까 이게 정확하게 뭔 말이냐면은 measurement 셋업이 정해지면은 피셔 인포메이션도 그거에 따라서 정해진다고 했잖아요.
예.
근데 여기서는 measurement를 바꾸잖아요.
예.
그러니까 요거를 바꾸면은 요 f 값이 바뀌어요. 그러니까 로어 바운드 값 자체가 바뀌는 건데
예.
이제 에스티메이터를 잘 조정해가지고 얘까지 만족시켰는데 이제 여기서 이 실험 셋업을 바꿔서 이 f를 더 낮춰주는 거죠.
그 밑에 보면 저게 맥스 값이니까 저게 더 작아진다.
그쵸.
약간 그런 저게 바뀌는 건 아니고
네네네.
저거의
예.
f의 최대값이 h니까
그쵸.
저 루트 f의 최소값이 저거다.
예. 그러니까 얘를 요 정도로 만들고 그 다음에 f를 바꿔서 더 낮추는
네.
거예요. 딱 그겁니다.
그럼 QVS를
예.
QVS.
마지막 슬라이드 한국말로 해도
네네.
그
요건가요? conclusion?
예, conclusion 그러니까 적어보려고 했던 건데
네.
그러니까 네거티비티랑 너무 네거티비티는 알겠는데
네.
그러니까 컨큐런스하고 퀀텀 지오메트리 디스콜드를 꼭 잡아서 그러니까 그런 퀀텀 파라미터도 비교하는 이유가 따로 있나요? 아니면 그냥 퀀텀 파라미터여서 뭔가 바운드가 더 작아지는 걸 보여주기 위한 그냥 여러 개 중에서 그런 걸 가져온 거거든요.
그냥 여러 개 중에 가져온 것 뿐인데 실제 논문 많이 읽어보면은 네거티비티랑 컨커런스가 많이 쓰이긴 하더라고요. 그래서 실용적으로 많이 쓰이는 그 퀀텀 인탱글먼트 퀀티피케이션 파라미터들을 가져와가지고 한 것 같습니다. 근데 지오메트릭 디스코드는 저도 왜 가져왔는지 정확하게 뭔지는 잘 모릅니다. 네.
그게 많이 보이신다고 했는데
네네.
그게 뭔가 좀 이유가 있나요? 그러니까 특정 셋업에서는 되게 많이 보이는 이런 거 있는 거.
그게
오버하게 좀 저기 많이 쓰는 거.
인탱글먼트 코스트나 디스틸레이션 약간 이런 다른 애들도 있는데 걔네들이 아마 이론적으로 계산하기도 매우 힘들 거예요. 그래서 계산이 그나마 용이한 것들 중에서 많이 쓰이는 것들이 얘네들이고 얘네들이 그리고 인탱글먼트 정도를 상당히 잘 나타내는 척도라고 사람들이 인식을 하고 있어서 그런 것 같습니다. 네. 네.
액티비티랑 모든 액티비티랑 차이점이
아까 잠깐 설명하고 넘어가서 놓치셨을 수도 있는데 네거티비티는 수학적으로 이렇게 디파인이 되거든요. 근데 로그는 그냥 거기다 로그 씌운 것뿐이에요.
이제 데이터 값을 좀 크게 확인하기 위한
그런 거죠. 실제로 로그 네거티비티를 더 많이 쓰는 것 같긴 한데 저도 논문을 많이 읽어보진 않아서 모르겠습니다. 네. 근데 이제 여기서는 피셔 인포메이션을 계산을 하니까 로그를 씌워줬을 때 그 계산 차이가 나긴 나잖아요. 그래서 그것까지 같이 해준 것 같습니다. 온라인에는 아직 질문이 없네요. 이제까지 질문을 받으면 되죠. 없으면 그냥 마무리. 예.
제가 마무리하겠습니다.
예.
Okay, thank you for your attention and thank again to today's presenter, Wonseok Huh. Okay, we'll finish the presentation. Thank you.